Okay, so we are graphing on our calculators in polar mode. Example number 2. Degrees are the most awkward unit.
They're so lame.
I don't know what y'all are talking about.
Here, hey, I want to do a number of things with this today. Hey guys, listen up, please. So again, please don't write in like really large letters and numbers here. I am going to kind of scooch off to the side. Believe it or not, this main question that's being asked here isn't going to take a whole lot of time or space if we don't want it to. And so I'm going to try to do a number of things with this. So this Rose does one of these, correct?
Don't mess it up.
That wasn't as good as that other one, but that one was okay. Okay. You know what? I am going to...
You don't, Meg? You haven't been here. You don't get a say.
I'm actually going to retry that because of the nature of this question. Let's see here.
So, can you explain what the pole is?
Well, so that's why I'm actually trying to redo this. So I wanted to make sure I pretty much go exactly through the origin. I was off by a little bit before. Okay. So, hey guys, some of this can be brand new. Make sure you pick this up first time. So it says, find all the rectangular equations. When you see rectangular equations, what on earth is that talking about? X's and Y's, yes. X, Y, coordinate system. So in the end, it's going to be Y equals blah, 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 X. Maybe, we'll see. And then so we're finding the rectangular equations of all tangent lines. And then this phrase over here, at the pole. So when you see the word, the words the pole, what are we talking about? That's polar speak for the origin.
So that's just where r equals 0.
Oh my goodness, yes, that's exactly what we're going to be looking at. So if we are looking for the equations of the tangent lines at the pole, we are talking about when this graph is at the pole, right? And so if I were to point out some points here, I think we'd be able to figure out which ones are or not at the pole. So do you see how this yellow point is not at the pole? All right. See how this one's not either?
Yeah. Wow.
Do you see how this one is?
Yes.
So as we trace this graph, so we're literally talking about when the graph is tracing over the origin, like going right through the origin.
Oh, so that one.
So there are a couple of different scenarios for this, right? Let's predict a little bit. So I'll use a red. No, I'll stick with yellow. Would you guys agree with me that in all likelihood, the x-axis is tangent to the graph at the pole?
Yeah, it sure is.
How about this line right here? Does this make sense that this would also be tangent to our rows at the pole? And this, obviously, we're going to get some details in here, but just like visually, is this making sense?
Yeah.
Yep.
And then how about right about there? You can see I'm off by a little bit because they should all be meeting in the same place. So let's try that again. Right about there and right about there. It's a little better. Man, that actually looks kind of cool on my screen.
Wow.
Yeah. Something gets lost. Maybe it's the lights. Lights are too bright. Try that. Okay, so then the idea here would be to find the equation of those 3 yellow lines. Does that make sense? Just from a visual perspective. We have some work to do, but visually we're there. Okay.
Yeah.
So let's go back to something that Jack threw out there real quick. He said, he's talking about what does this at the pole thing mean? And I said, well, that just means that the graph is actually passing through the origin. And he said, oh, that's when?
R equals 0, yeah. When R equals 0.
When R equals 0. And this is something that's easy just to blast right through because don't we set things equal to 0 frequently?
Yeah.
But let's understand the significance of this. If R is 0, that means you are actually just sitting right on the origin. And since the origin and the pole are synonymous, these would be the angles we're looking for. Like, what angle are you pointed towards when the radius is 0? You're at the origin. You're at the pole. Okay, so let's write that down. I would say 0 equals 2 sine of 3 theta. And this is where your incredible unit circle skills pay off big time. What would I do first, even before I did unit circle?
By 2.
Yeah, we get to 0 equals sine of 3 theta by division. And then how do I even really get to the unit circle idea? I have to do kind of one more step. How do I get the 3 theta isolated?
Inverse sine of 0.
Yep, that's right. So I get inverse sine of 0 equals 3 theta. So we're ready for those incredible unit circle observations here. For what angle or angles is sine 0?
0.
Okay, so let's see. He's saying 0, pi, 2 pi. Are those all right? You okay with that?
Yeah, but that's not Julian tree, so that's not what we're plugging in the theta. It only goes to pi.
We got to be really careful with this. So I found that this is something, I've talked with our pre-calc teachers a lot about this, and I want to make sure you all understand this. When your input is not just theta, like in this example is 3 theta, going around the circle once is usually not enough. Or let me put it like this, like you want to make sure that you go a little bit too far and then pull back, then not go far enough. Does that make sense? Because you can always stop and say, whoa, that answer is outside my domain versus, well, I only went to here and I should have gone there. So if this, let me put it like this. Yeah, well, let me put it like this. So back in the day when you're just doing pre-calc questions and they wanted you to solve some trig equation for theta, didn't they always give you some domain like 0 is less than or equal to theta, which is less than or equal to 2 pi or something like that?
Yeah.
Do you remember those? They would say, solve this equation for this domain. So if that's your domain for theta, what you'd actually need to do is do this. If you wanted to catch all the angles, you would need to multiply each one of those pieces by 3. So you'd go 0 is less than or equal to 3 theta, which is less than or equal to 6 pi. So you'd actually go around the circle 3 times, and then you'd divide by 3 and all this. We don't need to go that far. Here's what I'm thinking. I'm looking at my picture. Aren't there 3 distinct tangent lines here? So why would I do more than 3 unique angles, right? This should get me covered. Now, if you had doubts, you just keep going and you do 0 pi, 2 pi, 3 pi, 4 pi, etc. And at some point after probably that 2 pi, you'd find that you're getting an overlap. You're getting like the same answer. So you'd know that you should have stopped sooner. But don't stop short, right? Definitely don't stop short. Okay, so we don't need this stuff up here right now, so I'll get rid of that. Anyhow, so now we need to actually solve this. And so I would divide everything through by 3. I'd get 0, pi over 3, and 2 pi over 3 equals theta. And especially while we're kind of trying to get this figured out, I think it's really useful to try to visualize and see if it actually makes sense based on our picture, based on our graph. So when theta is 0, are we not talking about this direction in orange? You see how that would actually, like that direction would cause a tangent line that's through the pole for 1, but then tangent to the graph right there. How about pi over 3? Isn't pi over 3 pointing right about that way? So I just want to make sure, like visually, this seems reasonable. Like these angles actually make sense. And then 2 pi over 3 would be pointing that way. And so again, hopefully visually we're like, okay, this is possible, right? This is realistic at least. Okay, let's see here. I always debate about this. Do you all want to see the easy button first, or do you want to see the more circuitous route?
I would love to see a more circuitous.
Oh, I think that's
There's,
You're talking about finding dy dx.
yeah. So based on the nature
I say
of
do
this,
the hard part and then make them
so I'll tell you what, let's do, so we have 3 lines up here, right?
Yes.
Let's do one of them the difficult way. Then I'll show you how that could have been done the easy way and explain why. And then I'll let you guys do the other ones the easy way or however way you choose.
Done.
Okay.
Lovely.
So here is one thing that I think is important to consider that actually will make the overall issue here easier. And that is the fact that don't all of these tangent lines go through the origin?
Yes.
So what is going to be the y-intercept of all of the lines?
0.
0. So really the issue kind of goes back to what you said. If we just find the slope, we're basically done, right? So using all the stuff you guys have up around on our boards here, I'll just copy it down from up there. So I'm going to say, I'm going to start off with, I'll go backwards here. Yeah, I'll go backwards. In fact, I'll color code this a little bit better. I'm going to do this one right here. I'll do this orange line. So I'm going to do the 2 pi over 3 direction first. Okay, so here we go. I'm going to say dy dx at, are you confused, you say? Oh, okay.
No, I was just asking a question, but I'm good. I got it.
Oh, okay. I just want to make sure you're doing okay. Let me know if you're not. Okay, so I'm going to use these lovely dy dx formulas that you all have put around the boards. So let's see here. Dy dx at theta equals 2 pi over 3. Well, that would be f of 2 pi over 3 times cosine of 2 pi over 3, so on and so forth. And we're just going to fill all these guys in. And then we're going to get into our unit circle awesomeness.
Oh my gosh.
Some of these are duplicates, of course, so that'll make it a little bit easier. Oh, there should be a prime.
Shouldn't it be on the prime?
I'm looking at the black one that up there. I don't see a prime.
There, it's just really weird.
Okay,
See,
there we
that's
go.
thick. That's supposed to be prime.
Okay,
Disregard. Sorry, guys.
it's all right. It kind of just bled right in there.
Never heard of it.
Ooh, brutal.
You know what, Jack? You're not
Rough
doing it 'cause
crowd.
there's a minus in front of the F on the bottom.
I'm helping you.
Yep,
Oh,
Okay,
okay,
fine. You just put it moved in.
I was
I moved it out front instead of
Sorry.
buried in there.
That's all.
Okay, so let's see here. F of 2 pi over 3. So that means we need to plug in a 2 pi over 3 into our original radius equation. So that would be sine of 2 pi. And what's the sine of 2 pi? Oh my goodness, isn't that awesome? That makes that whole first term 0. That's kind of cool. That'll make things a little bit easier. Plus, okay, so then what's f prime?
Oh.
6 cosine 3 theta.
Yep, I'll put that up here just for a reference. I'll say r prime equals 6 cosine 3 theta using the chain rule there. Okay, I think this will work out nicely though. So if I plug in 2 pi over 3 into that, don't I get cosine of 2 pi?
Which is 1.
Times 6 is 6. Okay. Times sine of 2 pi over 3. What's that?
Wait, sign up.
Sine of 2 pi over 3. It's like sine of a 60, right?
Root 3 over 2.
There it is, root 3 over 2, and it's positive.
Yeah.
So times root 3 over 2.
Dude, you're so good.
It's not a big deal. I'm like stuck.
Okay, this is where we can be efficient with this. Do y'all remember what f of 2 pi over 3 is from above?
0.
So that lower left term all goes to 0. Plus, and I already know that f prime of 2 pi over 3 is 6 from my earlier work, so I don't have to redo all that. And then what's cosine of 2 pi over 3?
Negative 1/2.
Yeah, negative, it's negative, right, because we're in the second quadrant.
Yeah.
So negative 1/2
Oh, yeah.
makes sense.
3 root 3 over negative.
So let's see here. Wouldn't the 6's cancel out? And wouldn't basically the 1/2 and the negative 1/2 cancel out just to be negative 1? So I'm coming up with negative root 3.
All of that
That makes a lot of sense.
You know what's,
The
cra-
answer is
you know what's
negative
crazy?
three.
Is since it goes through you, so you can skip all that and just look at the line and say.
So yeah, but let's make sure we preface. That's going to be the easy button. Let's make sure we preface that with the what are we doing and why can we do it in this situation? Because people will often take that and they will run way too far with it. So let's wrap this one up and we'll get to that because you're totally right. So remember, like, what does that number mean? Like, what's the significance of that number?
The slope of the line.
Yeah,
To the graph.
there it is. So my first one would be, and here is answer number 1, would be y equals negative root 3 times x, technically plus 0, because of the y-intercept being 0. Obviously, we don't have to write that. And that would be that orange line, and I'll fill this all the way in. This orange line here fully is described by that equation.
Wow.
Okay, so let me piggyback off what Jack said because this is where I would want to take you here. I would really hope that if I showed you this question on some quiz or test, I'm really hoping that you wouldn't do what I just did in orange. I'm hoping that you would do what I'm about to do here in blue. Let me start off by saying this is one of the most misused things, one of the most misused strategies because it feels so easy, and it is, it really, honest to God, is, but it only applies when the line that you're trying to find the equation for is also directly mimicking the angle that you're using, right? So the fact that the angle and the line are the same thing means that I can do this. Maybe you remember this from before. Here's the relationship. Tangent of theta equals dy dx. So because the angle that we're using is also effectively the tangent line itself, we can do this. And that really comes down to the fact that these tangent lines are going through the pole. Like, so that's kind of the key here is if we're talking about tangent lines at the pole, since we measure all of our angles from the pole, then all of these angles would also be exactly representative of the lines we're trying to find. And so we can actually find our dy dx. Let me finish this real quick and I'll get to your question. All you really have to do is say, all right, well, my first angle is 2 pi over 3. So I could find my slope by just doing tangent of 2 pi over 3. And tangent of 2 pi over 3 just so happens to be negative root 3.
Oh, I like the other way better.
Well, you're
Okay, you're wrong.
be prepared to run out of time on a quiz or a test, but you're welcome to use that if you want.
That's the thing where it's like theta equals pi over 4. Like how that
If you thought about that as a line going through that angle, that would also be the tangent line in a case like this, right? Because we're talking about tangent lines through the pole.
Because like, well, I was thinking of it in terms of if we have the polar equation theta equals pi over 4, it mimics the
That's a line.
of x.
Exactly. Exactly. It's a line at that angle, whatever that angle happens to be. Meg, your question?
So if it's not going through the pole,
Can't do this.
you can never do it. There's never a time to do it.
Correct. It would not lead directly to the answer if you tried to do it in any other situation other than this. That's why I say, people run with it, and you can see why they're like, oh, why would I do that whole big mess of things? In this case, you wouldn't,
The only reason we can do it is
because it's through the pole. That's right. The line is the angle. Exactly, yeah, they're like right on top of each other. In every other instance, that will not be the case, unless it's some random coincidence, which I don't think would happen. I don't know. It would be very random.
Okay.
Okay, so why don't you guys see if you can use those other two angles to find the equation of the blue tangent line and the equation of the red tangent line. Like so.
Are you guys plotting points for it?
It was like supposed to be blank. The one where theta equals 0 is really hard. I couldn't even think of that.
Yeah.
Keep adding seconds.
I had to take you back to Mr. Scott's zero slope equals no fun when you're skiing.
0?
Zero slope equals.
See, Justin, remember?
Oh, that's my thing.
Oh, Mr. Scott just credited you.
Come on, Mr. Scott.
Might want to go march down.
And you know what happens when you try to ski a vertical slope?
You die.
You get undefined.
Yeah. Your life becomes not your soul.
Or you'd get X'd out.
Essentially.
X equals.
Yeah.
Why would I ski it? Boring. I'm with you. I love that.
No slope, no fun.
No slope, no fun. Yeah, but you gotta be careful with that because no slope technically means vertical.
Oh, so it's no fun to die.
Zero slope means zero fun. No slope means no more you.
Okay. I think we're getting a little bit lost in the sauce here.
The analogy can get a little bit, yeah. That's why I just say X'd out. Why would I ski it? That would just make me hungry. I'm like, what are we cooking and what kind of sauce is this?
Because we really were.
Football game tonight, we got chicken wings. So I'm excited.
Situation.
Okay, so here's how this could go. If we are trying to do this the easy way, for my second angle, which is pi over 3, I would say dy dx equals tangent of pi over 3. And when you evaluate, guys, listen up, please. When you evaluate tangent pi over 3, don't you get root 3? And so the blue tangent line, you'd get y equals root 3 times x plus 0. And then the last one in red there, aren't we really hoping that we get something that indicates a horizontal line?
Yeah.
Okay, so I get dy dx then equals tangent of 0, and that is 0. And so we then say, all right, well, what kind of a line goes through the pole and has a slope of 0? Well, wouldn't it have to be a horizontal line at 0? So that would be y equals 0. And we've got all 3 of them. I tried to color code it mostly. Is this making sense? Okay. So I would like to, the effort here is to help you guys get a little further down the road, but then also as a cautionary tale against overusing. So I hope you left a little bit of room, because I'm going to have you guys do something else with this. Yeah, we're going to do something else with this. We'll get to area on Wednesday and Thursday of this week. Don't worry. That'll be fun. So here we go.
Yeah, well, at least I didn't kill him. You know what? You literally killed
Not as many as Australia.
So here it is. Find the equation. Please pay attention so you can ask a question if you're not sure what I'm talking about. Find the equation of the tangent line at the end of the pedal in the first quadrant.
Okay.
Find the equation of the tangent line out there at the very end of the pedal in quadrant 1. And so I thought visually I would show you what I'm talking about. It's going to be this purple line. No, purple's a bad color. We'll make it a...
I was going to say yellow.
yeah, yellow's hard to see. Why am I running out of colors here? Come on. I'm going to go with... I'm going with light... Yeah, white. I'm going with light blue.
Where?
So I'm talking about
I'm not
this...
going to tell anybody because I just realized.
I mean,
I've already had the epiphany.
Talking about more or less that. Okay, that blue line segment.
when does the 10 theta thing work?
So it only... It only directly works when you've got a tangent line going through the pole, and that's because we measure all of our angles with the fixed end at the pole, and we rotate around
How do we
that.
find when there's a tan and it's not vertical or horizontal?
We need to find the angle. So
Be excited about that.
Because like before we were finding like where
So-
all the horizontal and vertical tangents were, and we could use the equation to find the angle at which the vertical.
yeah. We just set the top equal to 0, the bottom equal to 0.
If you like look at the triangle.
So the key here is the phrase like at the end of the pedal. So maybe I need to give you a little hint here.
No, no hits.
No, I already got it. You don't give them the rest of the hint.
So
because
think
they
about
could be little.
at the end of the pedal. That's so key. Like if you understand what at the end of the pedal, like if you can come to understand what that means, then you'll be able to do something with R, which will then get you to an angle, and then you'll be in pretty good shape.
Bro, so I don't know what I'm doing.
Well, let's give the folks that want to go a little further with this before I start laying down the heavy hints. Let's give them a chance to go a little ways.
Do I really have to do
Wait,
one?
it's.
Oh my god. We've already all been there. Calm down. So this is where my non-unit circle skills really come into play.
I drew in a little dotted line. Does that help? So number of ways. Number of ways to get there.
No, you weren't. I was.
We better get the rankings board up there. Get this official. Who was first? Who was second? Who was third? So here's the deal. When you're out there, the key is to figure out the length of R. It's 2. See, when you're at the end of the pedal, R is 2.
No, I said it equals.
When basically you want to answer the question, when R is 2, what's theta? That's going to come from setting something equal to each other.
But if you like this, it's 8.
How do I personally know this too? Like when you have a rose, whatever number is out front there on the coefficient, that's how far it is.
Oh, okay. So like
We plotted a bunch of points last
I have
time,
the plotting, so like that's
and
checks that. So
we had like sort of talked about that a little bit. And we played a lot on our calculators. That's maybe one thing you didn't do is we said, hey, what if this was a little bigger or this was a little smaller? What does that do? And we were able to figure some of those things
Hey,
out.
what was the way that you were doing it? 'Cause I was doing it differently.
What was I was doing what?
Like the way that you were explaining to magnitude.
Oh, I just
So
said
that's really different.
when. So it says at the end of the pedal, like up there at the very end. So
Oh.
at the end, R has to be 2.
Yeah.
It's like the furthest we could be from the pole.
Okay.
And so I just said, hey, if R is 2, and I know that R equals this, well then I could find this theta, I could find this angle here
that was like
by setting R equal to 2.
Okay.
and if like this thing is a 2, then they would be
So let's make sure that we're all on the same page. I think this would be a good place to start. 2 equals 2 sine of 3 theta.
Got there. Got that.
Because when you're out there at the very end of the pedal, you are the maximum distance from the pole.
Oh,
Maximum distance is 2.
did the first derivative.
Oh my goodness, that's so awesome. I'm just basing it on, hey, we know the nature of a polar graph.
Did you do the first derivative test?
But you could totally
Yeah,
do that.
totally.
You could go r prime equals 0.
Yeah.
You could totally do that.
Oh, I did
Absolutely.
I did it.
Jack, we're gonna figure this out together.
No, I did.
R equals 2.
R equals 2, yeah, that's what I did. I just said, yeah. So something interesting here, if in the instructions, if it said like, and you must justify your answer or something, then you're probably going to have to go to this whole first derivative, second derivative test concept and say, well, the maximum distance indeed is 2 because, and do a first derivative test or a second derivative test. That's actually really great reasoning. It just didn't say justify your answer, so I don't think I'm going to go there here. I'm just going to show some work to get there. That's some good thinking. Did anybody come up with the angle yet when you divide by 2 and then do the unit circle thing? Now think about that. Doesn't pi over 6 make a lot of sense based on what we just did? So if that angle to get us back to the pole was pi over 3, well then wouldn't halfway between 0 and pi over 3 be out there at the end of the petal of the rose? By symmetry, you would think, okay, yeah, halfway between, well, pi over 6 is halfway between 0 and pi over 3. Does that make sense?
So Santi cheated?
I just
Santi cheated? I don't think so.
So I found the angle different.
How did you find the angle?
You split it in, so it's like 3 petals. So I mean, there's a third, 360 degrees in between each one, and the bottom petal is at an angle of 3 pi over 2. So you add 2 pi over 3 to that, and you get the original angle.
Yeah. So you just use slightly different reasoning. I'm fine with that.
Does the other way work?
I don't know how we did
Yeah.
it.
That's totally fine.
How do you find
Yes, ma'am.
Thank you.
I wanna know if I'm right.
Okay, let's find out. Okay, so here's one way to do this. dy dx.
Also,
We could use our lovely formulas here. So I'm just looking back here in the back. I think they all look pretty good. I think so. Pi over 6 is by angle. So if I plug in a pi over 6, I get sine of pi over 2, which is 1 times 2 is 2. So there's my f of theta. Cosine of pi over 6 is? And I'm going to, hey, by the way, I will continue to just kind of try to prod you guys into thinking about that unit circle just because you have to be good at it. And so if you will just keep participating like you are, that's great. Okay, plus, and then I've got sine of theta. So what's sine of pi over 6? That's 1/2 times f prime. So that would be that 6 cosine 3 theta. So that would be 6 cosine of pi over 2. And what's that? 0 cosine of pi over 2. You love it when one of these factors is 0. Over, we're plugging pi over 6 down there. So again, we know that f of pi over 6 is 2. And now it's going to be sine of pi over 6. Say again? Oh, it's negative, right? I'll just put the negative out front. And it's 1/2. And then I think we probably get a 0 over here again, correct? Because we've got that f prime of pi over 6 again. Okay, so this equals what? Negative root 3? Negative root 3? Okay.
I have a shortcut that works for that.
oh, I did, I was.
Did you do dy dx and perpendicular it?
Yeah.
Yeah, you can do that too.
Oh, I just assumed it was going to be parallel to
You
the
mean,
other one.
oh, really? Oh.
Because it looks...
Be careful with it looks,
oh,
right?
No, that's why I did it the real way, or like this way. But
Yeah.
I was like...
So Aiden, say your way because your way works too.
It's since it's at the end of the petal, it's perpendicular to the original
Yeah.
angle.
It is perpendicular to it.
That's
So you could find the slope of that dotted blue line and then just opposite reciprocal it
so,
to get to the same thing. Yeah.
So you got one.
And again, you're still using unit circle stuff. I mean, is it slower? Is it faster? I mean, maybe it's a little faster. We could debate, right?
I just did it with the angle. I just subtracted 90 from the angle and then did that in the
That's
tangent
dope.
thing.
I
Yeah.
love that.
Yeah. Okay. So then the other thing we got to realize here about this one is this line does not go through the origin. So I can't just say, hey, it's y equals negative root 3x. I mean, you can see that the y-intercept is definitely not going to be 0. So how on earth...
The y-intercept?
I need to find a point. In fact, I think probably your best bet is going to be to find this bright green point, this point of tangency that I'm sort of bright green. How do you think we could find that point of tangency to wrap this up?
Well, we have two. We know the length of that, of the radius.
X
is 2.
equals R.
Oh, interesting.
And it's
I was going to go that route. I was going to go x equals r cosine theta, y equals r sine theta. But you actually could make a triangle, right? Knowing that the hypotenuse is 2 and the angle is pi over 6, right?
That's what I was thinking.
So much effort.
Yeah, you could do that too.
But it's the same thing.
It should give you the exact same answer either way. It is truly
So
the same thing.
hypotenuse is
I'll show you the official way. So x equals r cosine theta. So that would be 2 sine of 3 theta
Yeah,
times
that would be a cosine.
Never mind, sorry.
cosine
that's
theta,
embarrassing, guys.
right?
No, wait, yeah.
r, so r is the 2 sine 3 theta. So then if I plug in a pi over 6, let's think this through. My x coordinate would be 2 times, will be sine of pi over 2 after I do the canceling, so that's 1. So that's nice and easy. And what about cosine of pi over 6? That's the root 3 over 2. Yeah.
That's embarrassing.
It's all good. Okay, so that point is root 3, and y is equal to r sine theta. So it would be 2 times, and again it's going to be 1. And then what's sine of pi over 6?
Is it 1/2 this time?
There's our 1/2. Yep. So that's 1. So then my final linear equation for this tangent line that I asked you to find would be y minus 1 equals negative root 3 times x minus root 3. So I'm going to use point slope there just to make it easier on myself. But then, yeah, so that there in the purple box would be that equation of the tangent line. So I guess we could simplify a little bit. I guess the y-intercept would be 4, wouldn't it? Yeah, because you'd get, once you distribute, you get plus 3, and then you go plus 1, so you'd get 4. Who knew? We do now. Yeah, so I thought, I'm just trying to give you as complete of a picture as possible. I don't want you to think, oh, I'll just use the trick, or I'll never use that little trick. There are certain ways that you can be smart about it and use it to your advantage, the whole dy dx equals tangent of theta thing. It can be used in the wrong way, so just be careful. I'm trying to get you to understand like what it is so that you can use it correctly.
I think there's another trick you can do with that.
So let's just say what you think. Let's hear it.
Speak your truth. Since that radius is pi over 6 up, you can make a triangle with the y-axis, the radius, and then the tangent line, and you can probably find the y-intercept point.
So let's see here. So you're talking about like extending this up to the, if I could match it up, that'd be awesome. Talking about extending that essentially.
Yeah.
And
That sounds like a lot of effort.
I mean, it's
so this, let's just call this a different way.
Actually, hold on, we can do it. Let me think about it. 90, yeah, so we got a,
So if that's
a 36
perpendicular,
90.
2 root 3.
well, you could use this other little triangle down there too,
This one.
right?
Wow.
You could
Math
use
is wild,
So it's
man, I
4.
tell
So
you.
it's actually 4.
Yeah,
Yeah,
it's a 36
which is
to 90.
the actual
The y-intercept is 4.
y-intercept.
Why is this 4?
Dude, that's crazy.
So I don't know. You could call that a shortcut or just a different way. I don't know. They're all roughly the same amount of time, but
You
they're.
just want to do a little geometry.
I think anytime you can make a connection between something different or unexpected, I think that's good. Nice find for sure.
I miss Michelle.
Okay.
It did deserve a bad high five. It's okay. I was in middle school when I took the option.
Well, let's.
Really got a date.
Hey, let's wrap up our day with a brief foreshadowing of Wednesday and Thursday. So if you would, flip over, and I want to just kind of, like I said, just a little foreshadowing.
That's why I'm bad at it.
I think this is important so that when you come back, it's a little bit more of just a slight remembering versus, hey, I've never seen this before. So when we found areas under curves before, it was all rectangular stuff. And what geometric shape did we use to help us get there?
Rectangles.
Rectangles. That's right. In polar, it's not what we do. When finding the area within a polar curve, so rectangles goes here. But when finding the area within a polar curve, we will actually use something called a sector. Have you ever heard that word before?
It's not
Oh,
like a
is it
slice
like-
of pizza.
It's like a piece of pizza, a piece of pie, right? So it's like a slice of a circle,
Yeah.
right?
Interesting.
Because it can't be.
So I'll just give you a brief example
It's like you have to.
using,
Oh, that's going to
That's gonna be tough.
That's gonna be tough.
using a kind of a deformed cardioid there.
Where that area of the circle.
Hey, listen up, please. Do y'all see, oops. Do you guys see how if I tried to use rectangles here, it's a really confusing mess,
Yeah, that's.
right? I mean,
Yeah,
It
not
just sucks.
ideal.
That just sucks.
That
It's like you'd have to convert the polar curve over to rectangular, and then you'd have like the upper half and the lower half. And as you know, since x equals r cosine theta, y equals r sine theta, when you start converting those things and differentiating them, then they just go from here to here to here in complexity. So what we do, and you're going to find this, I think, to be fairly straightforward for you, is we try to cut out little pieces of pizza or pie. So what we do is we establish a radial line and another radial line, and then we find the area of that sector. Now what's challenging about this is a sector is explicitly a slice of a circle, and so that curvy outer edge is circular in nature, right? And these cardioids and lemniscates and things like that and you're actually going to see it here pretty well. Those are not really circular in nature, right? They don't have the same kind of a bend to them. And so we have these wonderful little slices of pie or pizza or whatever, these sectors. If I really wanted to find the full, true, exact area, how many of these little sectors would I need? And I'd squeeze them down so that they're really, really, really skinny, so that this central angle is approaching 0. We could fill this shape perfectly and get the exact area. We're talking about integrals, aren't we? Okay.
Here we go.
Yeah. All right, I'll see you guys on Wednesday. Have a good day.